Imagine a single teaspoon of material so heavy it outweighs an entire mountain. This isn't science fiction, it's the reality of neutron stars, where matter is packed so tightly it defies everything we know about the physical world. Across the universe, there exist places where gravity doesn't just bend the rules, it shatters them entirely, creating objects so dense they warp space and time itself. From the crushing depths of black holes to the unimaginable pressure inside white dwarfs, the cosmos is filled with extremes that challenge our very understanding of reality. What if I told you that some of these cosmic heavyweights are so extreme, light itself can't escape their grasp, or that a sugar cube-sized piece of a neutron star would weigh billions of tons here on Earth? These aren't just fun facts, they're glimpses into the most violent, mysterious, and awe-inspiring corners of the universe. And today, we're diving deep into 25 mind-blowing facts about these extreme densities, uncovering secrets that will make you see the cosmos in a whole new light. This journey isn't just about numbers or scientific jargon, it's about the stories these celestial monsters tell. How do black holes form, and what happens when two of them collide? Why do neutron stars spin faster than a kitchen blender, and what cosmic alchemy happens in their cores? Each fact we explore will peel back another layer of the universe's most intense mysteries, revealing a world where the laws of physics are pushed to their breaking point. So buckle up, we're about to venture into the heart of cosmic extremes, where the universe gets weird, wild, and utterly unforgettable. Neutron stars are the universe's ultimate cosmic pressure cookers, where gravity wins in a relentless battle against matter. Picture this: when a massive star runs out of fuel, it doesn't just fade away. It explodes in a supernova so violent it outshines entire galaxies for weeks. But the real magic happens in the aftermath. What's left behind isn't just a remnant, it's a neutron star, an object so dense that a single teaspoon of its material weighs as much as 1 billion tons. To put that into perspective, scoop up a sugar cube's worth of this stuff, and suddenly you're holding something heavier than Mount Everest. How does something so unimaginably dense even exist? It all comes down to gravity's ruthless grip. When a dying star collapses, the sheer force crushes atoms beyond recognition. Protons and electrons are squeezed together so tightly they merge into neutrons, hence the name. But here's where quantum physics steps in like an invisible bouncer, saying no further. A strange rule called neutron degeneracy pressure kicks in, preventing the star from collapsing into a black hole. It's like trying to pack an entire stadium's worth of people into a single elevator. There's just no more room, no matter how hard you push. What's even wilder is that neutron stars aren't just dense, they're also cosmic speed demons. Some spin hundreds of times per second, faster than a jet engine's turbine. And their surfaces, imagine a crust smoother than the finest glass, but under it lies a sea of neutrons so compressed they behave like a single, bizarre superfluid. If you thought Earth's gravity was strong, try standing on a neutron star. You'd be flattened into a thin film of atoms before you could blink. These extreme objects are proof that the universe doesn't just push boundaries, it obliterates them. At the heart of a neutron star, physics as we know it stops making sense. Picture the core like an atomic nucleus but blown up to the size of a city. Here, protons and electrons aren't just closed together. They've been squeezed so violently they've merged into a swirling ocean of pure neutrons. This isn't just dense. It's matter stripped down to its most basic building blocks, packed so tightly that a single thimbleful would contain more particles than there are stars in our galaxy. But the madness doesn't stop there. Under such unimaginable pressure, scientists suspect even neutrons might break apart, dissolving into something even more exotic: quark-gluon plasma. This bizarre state of matter hasn't been seen anywhere else in the universe since the first trillionth of a second after the Big Bang. It's like the universe's original recipe, a soup of fundamental particles so hot and dense that the rules of ordinary physics no longer apply. Remarkably, we've actually recreated traces of these conditions right here on Earth. Giant particle colliders like the Large Hadron Collider smash atoms together at near-light speeds, creating microscopic bursts of quark-gluon plasma that last just a fraction of a second. These experiments are like cosmic time machines, letting us glimpse the same forces that might be raging inside neutron stars right now. Yet even our most advanced simulations can't fully replicate what's happening in those distant cores. Theories suggest the pressure might warp neutrons into strange shapes, rods, sheets, or even tangled spaghetti-like structures physicists jokingly call nuclear pasta. Some models predict zones where quarks roam freely, while others hint at superconductors so powerful they could generate magnetic fields strong enough to rip molecules apart from light years away. One thing's certain, neutron star cores are laboratories of extreme physics, where matter exists in forms we're only beginning to imagine. Every new discovery peels back another layer, revealing just how little we truly understand about the universe's most punishing environments. Some of the universe's most extreme objects also double as its most precise timekeepers. Pulsars are neutron stars that have taken density and turned it into dazzling cosmic performance art. As these city-sized remnants of dead stars spin sometimes hundreds of times per second, they blast beams of radiation from their magnetic poles like interstellar lighthouses. Every rotation, those beams sweep past Earth, creating pulses so regular you could set your watch by them. The first pulsar ever discovered, Pulsar B 1921, was initially nicknamed Little Green Men 1 because its clockwork signals were so precise, astronomers joked they might be artificial. But the truth was even more extraordinary. This celestial metronome was a neutron star spinning once every 1.3 seconds, its beams slicing through space like a lighthouse beam cutting through fog. What makes pulsars truly special isn't just their speed, it's how they've become universal laboratories for testing Einstein's theory of relativity. When a pulsar orbits another dense object, the extreme gravity warps spacetime itself, causing tiny delays in the pulses that travel through this distorted region. It's like throwing a rock into a pond and watching the ripples, except here, the ripples are in the fabric of reality. Some pulsars, like the famous double pulsar system Pulsar J0737, orbit so closely that their dance creates gravitational waves stretching and squeezing space itself. The precision of their pulses lets scientists track these distortions down to the millisecond, giving us front-row seats to relativity in action. And then there are the millisecond pulsars, old neutron stars spun up to dizzying speeds by siphoning material from a companion star. These cosmic flywheels rotate faster than a helicopter blade, their beams flickering hundreds of times per second with such regularity they rival atomic clocks. Networks of these pulsars may one day serve as galactic GPS systems, helping future spacefarers navigate the cosmos by starlight. Each pulse is a message from one of the universe's most extreme environments, a neutron star's heartbeat echoing across light years. And with every flicker, they're not just illuminating the darkness of space, they're shining a light on the deepest mysteries of physics itself. Black holes take cosmic extremes to their absolute limit, places where density doesn't just push boundaries, it erases them entirely. At their core lies the singularity, a point where all the star's original mass gets crushed into zero volume. That's not just dense, that's infinity squeezed into a pinprick of space, where the laws of physics as we know them simply stop working. But not all black holes are created equal. Stellar mass black holes, the remains of massive stars that collapsed under their own weight, might weigh a few times our sun yet fit inside a city. Then there are the supermassive monsters like Sagittarius A, lurking at the heart of our Milky Way. This colossus packs the mass of 4 million suns into a space smaller than our solar system. a gravitational titan so powerful it whips surrounding stars into frenzied orbits at thousands of kilometers per second. Here's the twist: despite their terrifying reputations, black holes aren't cosmic vacuum cleaners. Their gravity only becomes inescapable if you cross the event horizon, that point of no return where even light gets trapped. Outside that boundary, orbits are possible. In fact, stars happily dance around Sagittarius A for billions of years, their paths tracing delicate loops in the fabric of spacetime. What makes supermassive black holes even stranger is how they defy expectations. You'd think cramming more mass into a tiny space would make them denser, but the opposite happens. A stellar mass black hole singularity is unimaginably compact, while Sagittarius A, despite its enormous mass, has an average density comparable to air because its event horizon is so vast the mass spreads out. It's a reminder that in the universe's most extreme realms, the rules constantly surprise us. These gravitational giants aren't just destructive, they're creators too. The chaos around them births new stars, shapes entire galaxies, and may even hold clues to how the cosmos itself evolved. From the tiniest singularity to the supermassive anchors of galaxies, black holes prove that density isn't just about how much you pack in, it's about how space itself bends under the weight. The event horizon is the ultimate cosmic threshold, a boundary where the universe's rules take a sharp turn into the bizarre. Picture standing at the edge of an enormous waterfall, where the current grows so strong that even Olympic swimmers couldn't fight their way back upstream. That's essentially what happens near a black hole, except instead of water, it's spacetime itself being dragged inward at speeds even light can't match. Once anything crosses this invisible line, there's no going back, no signal, no last-minute rescue, just an inexorable plunge into the unknown. What makes the event horizon so fascinating isn't just its destructive power, it's how it warps our understanding of reality. Einstein's theory of relativity predicts that gravity bends spacetime, but here, the distortion is so extreme that all possible paths lead inward. Light struggling to escape gets stretched into longer, redder wavelengths in a phenomenon called gravitational redshift until eventually its photons fade into oblivion. If you were watching from a safe distance, someone falling in would appear to slow down, freeze, and dim near the horizon, their image smeared across time like a cosmic illusion. The Event Horizon Telescope's groundbreaking image of the black hole in galaxy M87 brought this shadowy frontier into focus for the first time. That glowing ring we saw, that's light bent so sharply by gravity it's circling the black hole like water spiraling down a drain. The dark void at the center isn't the event horizon itself, it's the point where even light's desperate loops finally surrender to the darkness. This shadow is a perfect match for Einstein's predictions, but the horizon hides even wilder secrets. Quantum physics suggests it might not be the smooth, mathematical surface we imagine, but a chaotic firewall of particles popping in and out of existence. Some theories propose that information about what falls in gets scrambled and ejected back out as holographic echoes. The event horizon isn't just a barrier, it's a laboratory for testing where relativity and quantum mechanics collide, revealing just how much we still don't understand about the fabric of reality. Spaghettification sounds like a pasta dish gone wrong, but it's actually one of the universe's most violent cosmic events. Imagine getting close enough to a black hole that its gravity pulls harder on your feet than your head. The difference in force would stretch you like taffy, thinning you into a string of atoms before you even crossed the event horizon. This isn't theoretical, it happens to stars that wander too close. Take Assassin 14, Li, a star that made the fatal mistake of orbiting a supermassive black hole. As it strayed into the danger zone, the black hole's tidal forces ripped it apart in a process called a tidal disruption event. The star didn't just break into chunks, it was stretched into a long, thin stream of superheated gas, swirling into the black hole like cosmic spaghetti. For months afterward, telescopes detected flares of X-rays as this stellar noodle spiraled inward, friction heating it to millions of degrees. But spaghettification isn't just about stretching. It's a brutal tug of war between gravity and the fundamental forces holding matter together. The black hole's gravity is so strong that it overcomes the atomic bonds in your body, or in a star's case, the nuclear forces that once kept it stable. Near smaller black holes, the effect is even more extreme. Their steeper gravity gradients mean the difference in pull between your head and feet would be far more dramatic. You wouldn't just thin out, you'd be shredded atom by atom, your particles stretched into a line of glowing plasma. This violent process isn't just a spectacle, it's a window into black hole physics. By studying the light from these stellar deaths, astronomers can measure black hole masses, spin rates, and even test Einstein's predictions about how gravity warps spacetime under extreme conditions. Every noodle-fied star is a cosmic experiment, revealing how matter behaves when pushed beyond its limits. White dwarfs are the quiet survivors of stellar evolution, the dense, glowing embers left behind when stars like our Sun exhaust their nuclear fuel. Unlike their more violent neutron star cousins, these stellar remnants don't go out with a bang but fade into a slow, ultra-dense retirement. Pack all the mass of a star into a sphere the size of Earth, and you've got the recipe for one of the universe's most extreme balancing acts. The secret to a white dwarf's defiance against total collapse lies in a quantum quirk called electron degeneracy pressure. When a star sheds its outer layers, what remains is a core so compressed that electrons normally whizzing around atoms get forced into uncomfortably close quarters. At these densities, they push back with unimaginable force, like a crowd packed into an elevator where no one can move an inch closer. This resistance isn't about heat or motion. It's pure quantum stubbornness, a rule that says no two electrons can occupy the same state. The result, a star corpse that refuses to shrink further, holding its ground against gravity's relentless pull. To grasp just how dense these objects are, picture squeezing an entire car down to the size of a raindrop. That's the kind of packing we're talking about. A teaspoon of white dwarf material would weigh several tons on Earth. Yet despite this crushing density, white dwarfs aren't just inert husks. Many glow white-hot from residual heat, slowly cooling over billions of years like cosmic coals in an endless twilight. Some even stage dramatic comebacks. In binary systems, a white dwarf can siphon gas from a companion star, igniting runaway nuclear reactions on its surface. These explosions, called nova, can outshine entire star systems for weeks. And if a white dwarf accumulates too much stolen mass, it crosses a deadly threshold, triggering a Type I supernova, a detonation so uniform astronomers use it as a cosmic measuring tape to map the universe's expansion. White dwarfs are proof that even in death, stars find ways to shape the cosmos. Their quiet persistence and occasional fireworks make them some of the most fascinating and deceptive objects in the universe. They may not have the flash of black holes or the speed of pulsars, but in their own way, they push the limits of what matter can endure. Deep in the cosmos, there exists a planet that would make even the most extravagant jewelers gasp, a world made almost entirely of diamond. Meet Pulsar J1719-1438b, a planet so dense and carbon-rich that its very core may have crystallized into a solid diamond larger than Earth. This isn't some interstellar fairy tale, it's the result of physics pushed to its most glittering extreme. This extraordinary world orbits a pulsar, the fast-spinning corpse of a dead star, where gravitational forces are so intense they rewrite the rules of chemistry. The planet probably began its life as a massive star, rich in carbon, that got ripped apart when its companion star went supernova. What remained was a core so compressed that carbon atoms, normally the building blocks of life, were forced into a rigid, crystalline lattice. Under pressures millions of times greater than Earth's deepest mines, those atoms aligned into a structure so perfect it could span continents. The conditions here are beyond anything found in our solar system. Temperatures soar high enough to vaporize steel, yet the diamond structure holds firm, its atomic bonds unbreakable even under such punishment. If you could somehow mine a chunk of this world, ignoring the crushing gravity and lethal radiation, it wouldn't look like the diamonds we know. This isn't the sparkly gem in an engagement ring, it's a dark, ultra-dense form of diamond forged in nature's most violent workshop. What's even more fascinating is how these planets form. Carbon-rich systems around pulsars are cosmic pressure cookers, where elements get rearranged in ways that defy normal planetary science. Some theories suggest diamond planets might be the remnants of white dwarfs that had their outer layers stripped away, leaving behind a crystallized core. Others propose they're the shattered remains of gas giants, their atmospheres blasted off to expose diamond interiors. These exotic worlds aren't just curiosities, they're proof of how extreme environments can transform matter into something utterly alien. And they're not alone. Scientists suspect the universe could be littered with diamond planets, each one a glittering testament to the cosmos's ability to turn destruction into beauty. The next time you admire a diamond, remember, somewhere out there, entire worlds are shining far brighter, forged in furnaces we can barely imagine. The universe may hold objects even more extreme than neutron stars, bodies so dense they dissolve the very concept of matter as we know it. Enter quark stars, hypothetical cosmic anomalies where gravity's crushing grip tears neutrons apart, reducing them to a swirling sea of their fundamental components. Picture a neutron star pushed past its breaking point, its carefully balanced quantum pressure overwhelmed until protons and neutrons shatter like glass, releasing a primordial soup of quarks and gluons. This isn't just dense, it's matter stripped down to its most raw, unfiltered state, a condition not seen since the universe's first microseconds. Astronomers suspect one candidate might already be hiding in plain sight. RxJ 1856.5-3754, a mysterious object drifting just 400 light-years away. At first glance, it looks like an ordinary neutron star until you realize it's far too small and dense to fit the usual models. Observations suggest it's barely 7 miles across, with a surface so hot it emits X-rays like a cosmic beacon. The math just doesn't add up for a neutron star unless its core has crossed the threshold into quark matter, collapsing even further under its own weight. What makes quark stars so tantalizing is how they blur the line between theory and reality. In these extreme environments, quarks, normally forever locked inside protons and neutrons, might roam freely, forming exotic states like strange quark matter. Some physicists speculate this material could be the universe's most stable form of matter, denser than anything else in existence. If true, entire quark stars could act like cosmic seeds, converting any neutron star they touch into more quark matter through a runaway reaction. Yet RxJ 1856 remains a puzzle. Its temperature, size, and energy output defy simple explanations, leaving astronomers debating whether it's a quark star, an unusually dense neutron star, or something entirely unknown. Every flicker of X-rays from its surface carries clues, hinting at physics too extreme for our current models. If quark stars do exist, they're not just scientific curiosities, they're living relics from the universe's most violent moments, proof that when gravity wins, it doesn't just bend the rules. It rewrites them entirely. Every star lives on the knife's edge between survival and destruction, but none face a more precise cosmic deadline than white dwarfs. The Chandrasekhar limit, 1.4 times the mass of our Sun, is the ultimate tipping point where these stellar embers either endure or detonate in one of the universe's most spectacular fireworks displays. This critical threshold wasn't discovered in some high-tech lab, but on a 7-day ocean voyage in 1930, when a 20-year-old Indian physicist named Subramanian Chandrasekhar scribbled equations that would rewrite our understanding of stellar fate. Chandrasekhar's breakthrough revealed the invisible battle raging inside every white dwarf. As these dead stars accumulate mass, whether by slowly siphoning gas from a companion star or colliding with another white dwarf, their electron degeneracy pressure fights to hold gravity at bay. But there's a ceiling to this quantum resistance. Cross 1.4 solar masses and electrons can't push back hard enough. In less than a second, the star's core collapses, temperatures skyrocket past 10 billion degrees, and runaway nuclear fusion rips through its carbon-oxygen fuel like a chain reaction of atomic bombs. The result, a Type Ia supernova so bright it can outshine entire galaxies, and so uniform astronomers use these explosions as cosmic yardsticks to measure the universe's expansion. What makes the Chandrasekhar limit so extraordinary is its precision. Unlike messy stellar explosions where outcomes vary, Type Ia supernova always ignite at nearly identical masses, making them the universe's perfect standard candles. This reliability helped reveal dark energy's existence when astronomers noticed distant supernovae were dimmer than expected, proof the cosmos wasn't just expanding but accelerating. Yet the limit isn't just about destruction, it's a cosmic balancing act. Some white dwarfs flirt dangerously close to the threshold, like recurrent nova Rs Ophiuchi, which erupts every few decades as it nibbles material from its companion. Others cheat fate entirely through rapid rotation, their spin spreading out the added mass like a figure skater extending their arms. Chandrasekhar's number isn't just a death sentence, it's a reminder that in the universe's most extreme environments, even the smallest margins can mean the difference between fading quietly into darkness and going out in a blaze of glory. Even neutron stars, the universe's ultimate pressure-resistant objects, have their breaking point. The Tolman-Oppenheimer-Volkoff limit, named after the physicists who first calculated it, is the cosmic line in the sand where even the mighty neutron degeneracy pressure can't fight gravity's relentless pull. Beyond roughly 2 to 3 times the Sun's mass, these incredibly dense objects can't hold themselves up anymore. The result, a catastrophic collapse into a black hole where matter vanishes from the known universe forever. This limit isn't just a neat theoretical prediction, it's a battleground where extreme physics meets the unknown. We know neutron stars resist collapse thanks to quantum mechanics, but their cores remain one of the universe's best-kept secrets. Unlike white dwarfs, where electron degeneracy pressure follows well-understood rules, neutron stars flirt with far stranger possibilities. At their centers, neutrons might dissolve into quarks, form exotic states of matter, or even transform into something entirely unpredictable. These mysteries mean the exact TOV limit isn't a fixed number. It shifts depending on what's happening deep inside. Take the case of GW190421, the heaviest neutron star ever detected. This monster weighs in at around 2.1 solar masses, right on the edge of the theoretical limit. Its existence forces physicists to reconsider what's possible in neutron star cores. If it's just neutrons holding this thing up, the math strains credibility. But if the core contains hyperons, strange quark matter, or other exotic particles, suddenly its stability makes more sense. Every massive neutron star we find acts like a cosmic lab experiment, testing the limits of physics under conditions we can't replicate on Earth. The uncertainty doesn't stop there. Some models suggest rapid rotation could temporarily push a neutron star past the TOV limit, spinning fast enough to delay collapse. Others propose that magnetic fields, trillions of times stronger than Earth's, might provide extra support. But these are just temporary reprieves. Eventually, gravity always wins, proving once again that in the universe's most extreme environments, even the toughest objects have their limits. The TOV limit isn't just a number, it's a reminder that density can only push so far before the cosmos demands a final surrender. Imagine a magnetic field so powerful it could strip the data from every credit card on Earth from halfway across the galaxy. That's the reality of magnetars, neutron stars turned up to 11, where magnetic forces reach levels so extreme they defy comprehension. These cosmic powerhouses generate fields measuring in the quadrillions of Gauss, strong enough to rip apart atoms themselves. For comparison, Earth's magnetic field is a cozy 0.5 Gauss, while an MRI machine hits about 15,000. A magnetar, try 1,000 trillion times stronger. The origin of these terrifying magnetic monsters lies in their chaotic birth. When certain massive stars collapse into neutron stars, their already intense magnetic fields get squeezed and supercharged during the supernova explosion, like twisting a rubber band until it snaps, except this snap amplifies magnetism to unimaginable levels. The result is a stellar remnant so magnetized it warps the very structure of space around it, creating an environment where the laws of physics start to fray at the edges. But magnetars don't just sit there quietly, they unleash their fury in violent eruptions called starquakes. Picture the crust of a neutron star under unimaginable strain from internal pressures and external magnetic forces. When that crust finally cracks, the energy release is catastrophic. In December 2004, a magnetar 50,000 light-years away in the constellation Sagittarius erupted with a gamma ray, burst so powerful it briefly outshone the full moon despite being halfway across the Milky Way. The blast ionized Earth's upper atmosphere, disrupting radio communications and satellite operations. If this had happened within 10 light-years, it could have triggered a mass extinction by stripping away our ozone layer. What makes these events even wilder is how fast they unfold. A magnetar's magnetic field can reconfigure in milliseconds, releasing as much energy as our sun emits in 100,000 years. Some theories suggest these fields are so intense they create magnetic knots that twist spacetime itself, creating temporary portals where matter behaves in ways we can't yet explain. Yet for all their destructive potential, magnetars are also cosmic gold mines for scientists. Their extreme conditions let us test theories about quantum electrodynamics in ways no Earth-based lab ever could. Every flicker, every starquake carries clues about how matter behaves under forces so strong they make black holes look tame. These stellar magnets remind us that the universe doesn't just push boundaries, it invents entirely new rules just to break them. At the smallest scales imaginable, far beyond atoms, beyond even quarks, spacetime itself might be boiling with chaos. This is the realm of quantum foam, where the smooth universe we perceive frays into a turbulent sea of fleeting black holes and wormholes. Picture the surface of a calm lake on a windless day. To our eyes, it's glassy perfection, but zoom in 1,000 trillion times and you'd find a frenzy of bubbles forming and popping in a frenzy. That's quantum foam, spacetime's hidden turbulence at the Planck scale, where distances shrink to a millionth of a billionth of a billionth of a centimeter, and time fractures into intervals so brief they make a nanosecond feel like an eternity. The idea emerged from the collision of two pillars of physics, quantum mechanics and general relativity. Einstein taught us spacetime bends like fabric under gravity's weight, but quantum theory insists everything, even empty space, must writhe with uncertainty. Combine them and you get a paradoxical reality where spacetime isn't smooth at all. Instead, it's a frothing mess of microscopic black holes blinking into existence, annihilating each other before they're even fully born. These aren't black holes as we know them, they're quantum fluctuations, so tiny their gravitational pull is negligible, yet their existence hints at a deeper layer of cosmic architecture. Hawking radiation plays a starring role here. Just as large black holes slowly evaporate by emitting particles, quantum foam black holes might form and vanish in a flash, their lifespans dictated by Heisenberg's uncertainty principle. Some theories suggest this foam could be studded with wormholes, ephemeral bridges connecting distant points in spacetime. These wouldn't be the sci-fi stargates of pop culture, but fleeting, unpredictable portals far too small for anything to traverse. Yet their mere possibility reshapes how we think about the vacuum of space, transforming it from an empty stage into a seething, dynamic participant in the universe's deepest workings. The catch: we can't observe this chaos directly. The Planck scale is so absurdly tiny that current technology would need to be a billion times more sensitive to detect it. But indirect clues abound. Some physicists speculate that if quantum foam exists, it might subtly alter the paths of high-energy particles from distant cosmic rays or imprint faint irregularities in the light from quasars. Others propose that gravity wave detectors like LIGO could one day spot echoes of these microscopic spacetime quakes. What makes quantum foam so revolutionary isn't just its strangeness, it's how it forces us to rethink the nature of reality itself. If spacetime is fundamentally foamy, then the smooth, predictable universe we experience is an illusion, a statistical average of untold quantum frenzies playing out beneath the veil. It's a reminder that even the emptiest reaches of space are anything but empty. They're a quantum storm raging where no telescope can see. Some black holes might be so small they could slip through your fingers, yet pack the punch of an entire mountain. Primordial black holes are a cosmic wildcard, hypothetical remnants from the universe's explosive first seconds. Unlike the stellar mass or supermassive black holes we know today, these could be as tiny as an atom but weigh as much as an asteroid, squeezed into a space smaller than a proton. Their existence would rewrite not just black hole physics, but potentially solve one of astronomy's greatest mysteries: the nature of dark matter. How could something so small form? The secret lies in the chaos of the early universe. Moments after the Big Bang, space wasn't smooth. It was a seething, uneven cauldron where density fluctuations could have been extreme enough for pockets of matter to collapse directly into black holes. No dying stars required. Picture bubbles forming in boiling water, except these bubbles are regions of space so dense they pinch off into microscopic singularities. Some might have evaporated instantly thanks to Hawking radiation, but those heavier than 1 billion tons could still be lurking in the cosmos today, invisible yet everywhere. The most tantalizing possibility: these ancient relics might account for the universe's missing mass. While stars and gas make up less than 15% of the matter we've detected, primordial black holes could be the hidden source of dark matter's gravitational pull. Unlike exotic particles we've never found, these would be ordinary matter, just compressed beyond recognition. They'd drift through galaxies like invisible ghosts, neither emitting light nor interacting with ordinary atoms. Spotting something so small yet massive sounds impossible, but physicists have clever ways to hunt them. When a primordial black hole passes between us and a distant star, its gravity would bend light like a lens, causing the star to briefly brighten, an effect called microlensing. Some researchers even suggest these tiny titans might trigger telltale flashes when they collide with neutron stars or emit gamma-ray bursts as they evaporate. If they exist, primordial black holes would be cosmic time capsules carrying secrets from the universe's first moments. They could be floating through your room right now, harmless yet holding the key to some of physics' deepest puzzles. From the infinitely large to the infinitesimally small, the universe never runs out of ways to surprise us. When two neutron stars spiral toward each other in a deadly cosmic dance, they don't just collide, they detonate in an explosion so powerful it forges the heaviest elements in the universe. The event known as GW 170817 wasn't just another ripple in space-time, it was a golden revelation. In August 2017, gravitational wave detectors caught the telltale tremors of two neutron stars merging 130 million light-years away. Just 2 seconds later, telescopes around the world picked up a gamma-ray burst, the birth cry of a kilonova, an explosion 1,000 times brighter than a typical nova. But the real treasure wasn't the light show, it was what that light revealed. As the neutron stars, each about the size of Manhattan but with more mass than our sun, slammed together, their unimaginable collision spewed out a swirling maelstrom of neutrons. In this neutron-rich environment, atoms didn't just form, they were assembled in bulk. A process called rapid neutron capture, or the R process, transformed these particles into heavy elements like gold, platinum, and uranium. The numbers are staggering. GW-170817 alone may have flung out hundreds of Earth masses worth of gold and other precious metals into space. That wedding ring on your finger, its atoms were likely born in a cataclysm just like this, billions of years ago. Detecting this event marked a watershed moment in astronomy, the first time gravitational waves and light were observed from the same cosmic event. The gravitational signal gave scientists the heads-up that something massive had collided, while the follow-up observations in everything from radio waves to X-rays painted a detailed picture of the aftermath. What they saw confirmed theories dating back to the 1970s, that neutron star mergers are the universe's primary factories for heavy elements. The aftermath of a kilonova is no less spectacular. The ejected material glows with a distinct reddish hue thanks to the radioactive decay of rare earth elements like lanthanides. Over days, this glow fades as the debris expands and cools, but the legacy lasts far longer. Those forged elements eventually become part of new stars, planets, and even life itself. Without these violent mergers, the periodic table would be missing some of its most iconic entries, and Earth's crust would lack the precious metals that have shaped human civilization. What makes neutron star collisions even more fascinating is how rare they are. In our Milky Way, they might happen only once every 10,000 to 100,000 years. Yet each one seeds the galaxy with enough heavy elements to enrich countless future solar systems. GW-170817 wasn't just a scientific breakthrough. It was a glimpse into the alchemy that makes our universe richer, proving that even in destruction, the cosmos is always creating. What if everything you see around you, the depth of space, the swirl of galaxies, even your own body, is nothing more than an illusion, a holographic projection from a two-dimensional surface at the edge of the universe? This isn't science fiction, it's the holographic principle, one of the most radical ideas in modern physics. The theory suggests that all the information making up our three-dimensional reality might actually be encoded on a distant, two-dimensional boundary, like a cosmic DVD storing the universe's entire data on its surface. The idea first emerged from an unexpected place: the study of black holes. When physicists calculated how much information a black hole could hold, they hit a startling realization. The maximum entropy, the number of possible states inside, didn't scale with its volume as you'd expect, but with its surface area. Imagine taking all the books in the world's largest library and somehow fitting them onto the covers alone with nothing inside. That's essentially what the math implied. The discovery led to a bombshell. Maybe the same applies to the entire cosmos. String theory takes this further, proposing that the fabric of space-time isn't fundamental at all, but emerges from a network of vibrating strings operating in fewer dimensions. Think of it like a movie screen. What looks like a three-dimensional scene is really just patterns of light on a flat surface. In this view, black holes aren't just cosmic vacuum cleaners. They're information processors, their event horizons acting like ultra-dense hard drives encoding everything that falls inside. But how could this possibly work in practice? One clue comes from quantum entanglement, where particles remain connected across vast distances. Some scientists suggest this spooky action at a distance might be the glue holding the holographic illusion together, with entangled bits on the universe's boundary creating the appearance of depth in the interior. If the holographic principle sounds mind-bending, that's because it is. It challenges our most basic assumptions about reality, suggesting that space, time, and even gravity might be secondary phenomena, side effects of something far stranger happening at the edges of existence. While we can't yet prove this theory, it's a powerful reminder that the universe's true nature might be hiding in plain sight, written not in 3 dimensions but 2. Before black holes ruled the cosmos, there might have been something even stranger: dark stars, hypothetical giants built not from ordinary matter, but from the universe's most elusive substance, dark matter. Picture a star so massive, so dense, that its gravity bends light into endless loops before it even forms a singularity. These wouldn't be the inescapable voids we know today, but luminous traps where photons spiral for millennia, struggling against a pull fueled by the invisible. The math behind dark stars reads like science fiction. Formed in the early universe, they'd grow by feasting on dark matter particles which, unlike regular matter, don't emit light or heat when colliding. Instead of nuclear fusion, these behemoths would rely on dark matter annihilation to power themselves, glowing faintly with an otherworldly haze. Their cores could reach densities that make neutron stars look fluffy, yet without collapsing into black holes, thanks to dark matter's unique properties pushing back against gravity's crush. Spotting these relics would require rewriting our cosmic playbook. Unlike black holes, which betray their presence through accretion disks or gravitational waves, dark stars might lurk undetected, their light too dim for current telescopes. But next-generation instruments like the James Webb Space Telescope could change that. By scanning the early universe for oddly cold, massive objects radiating just a whisper of infrared light, astronomers might finally catch a glimpse of these invisible titans. The implications are staggering. If dark stars exist, they could solve multiple cosmic puzzles at once, explaining anomalies in the universe's first light, the distribution of supermassive black holes, even the nature of dark matter itself. They'd be proof that the cosmos harbors forms of stellar life we've barely begun to imagine. And if they've already collapsed into black holes, then the monsters at the hearts of galaxies might have started their lives not as stars, but as something far more mysterious: ghosts of a hidden universe written in gravity alone. Deep inside every black hole, where general relativity predicts a singularity, a point of infinite density, there might instead lurk something far stranger: a Planck star. These theoretical objects represent nature's ultimate resistance to collapse, where matter reaches the Planck density 5.16 times 10 to the 96 kilograms per cubic meter and rebounds like a cosmic trampoline. Forget the idea of an infinitely dense point. Loop quantum gravity suggests black holes might contain a shrunken, ultra-dense remnant of the original star, compressed to a sphere just a millionth of a billionth of a nanometer across. This isn't just a tiny object, it's a relic from the Big Bang's playbook, a clue that black holes and the birth of the universe might share the same physics. The journey to a Planck star begins like any other black hole story. A massive star collapses under its own gravity, squeezing past the neutron star phase until even quantum forces can't hold it up. But instead of vanishing into a singularity, loop quantum gravity proposes that spacetime itself has a granular structure, a fabric woven from tiny, indivisible threads. At the Planck scale, these threads can't be squeezed further, creating a repulsive force stronger than gravity itself. The collapsing star hits this barrier and rebounds, but the process happens so deep inside the event horizon that no outside observer ever sees it. It's like a firework exploding inside a locked vault. The vault's walls, the event horizon, keep the spectacle hidden from view. What makes Planck stars revolutionary isn't just their refusal to become singularities, it's how they could solve 2 cosmic mysteries at once. First, their explosive rebound might explain dark matter. Some theories suggest the energy released during the rebound could manifest as weakly interacting particles, perfectly matching the missing mass we detect across galaxies. Second, and even more mind-bending, is their connection to the Big Bang. If a collapsing star can bounce back at Planck density, perhaps our entire universe did the same, emerging not from a singularity, but from the rebound of a previous universe's collapse. This Big Bounce scenario replaces the violent, inexplicable singularity of the Big Bang with a natural transition, like a phoenix rising from cosmic ashes. The most tantalizing clue might lie in black hole explosions. When a Planck star finally evaporates due to Hawking radiation, a process taking billions or even trillions of years, its pent-up energy could blast outward as a gamma ray burst visible across the universe. Some astronomers speculate that certain unexplained high-energy cosmic rays might be the dying screams of these primordial Planck stars, their faint echoes carrying secrets about quantum gravity's inner workings. While we can't yet probe inside a black hole to confirm Planck stars exist, their hypothetical existence reshapes how we view the universe's most extreme environments. They suggest that even in the face of oblivion, matter and spacetime fight back, refusing to surrender to infinite collapse. If loop quantum gravity is right, black holes aren't cosmic dead ends. They're hibernating engines biding their time until quantum physics lets them spark anew. Somewhere in the universe, there might exist a substance so dangerous it could rewrite the very fabric of matter itself. Strangelets. These hypothetical chunks of strange quark matter aren't just dense, they're the ultimate cosmic contagion, capable of transforming anything they touch into more of themselves. Picture a single droplet of this material landing on Earth. Within seconds, every atom it contacts could be converted, triggering a runaway reaction that turns our entire planet into a lifeless lump of strange matter. This isn't apocalyptic fiction. It's a scenario physicists have seriously debated, with experiments like the relativistic heavy ion collider even conducting safety assessments before smashing particles at near light speeds. Strangelets emerge from one of quantum physics' most unsettling possibilities, that under extreme pressure, ordinary matter might not be the most stable form. Protons and neutrons, the familiar building blocks of atoms, are made of up and down quarks. But in the bizarre world of quark matter, a third flavor, strange quarks, could dominate. Some theories suggest that at ultra-high densities, like those inside neutron stars, these quarks could form a strange matter phase more stable than anything in our everyday experience. If true, any chunk breaking free, say, from a neutron star collision, could act like a superconductor of destruction, rewriting matter's code wherever it drifts. The real controversy lies in whether we're safe from this cosmic alchemy. When scientists first proposed creating quark-gluon plasma in particle colliders like RHIC or the Large Hadron Collider, some worried the conditions might accidentally spawn a strangelet. The math suggests it's vanishingly unlikely. These machines don't reach neutron star-level pressures, but the stakes were high enough that teams ran exhaustive risk assessments. The verdict: even if a strangelet formed, it would evaporate instantly. But the universe has its own, far more powerful laboratories. When two neutron stars collide, the pressures involved dwarf anything we can recreate on Earth. Simulations show these mergers could briefly cook up strange matter, flinging it into space in tight, dense clumps. The good news: space is vast, and any wandering strangelets would likely lose energy over billions of years before reaching inhabited worlds. Still, the fact that this scenario exists at all reminds us that the universe doesn't just harbor wonders, it holds potential catastrophes we're only beginning to comprehend. Imagine flipping a switch that doesn't just turn off the lights, it turns off the universe. That's the terrifying possibility of vacuum decay, a doomsday scenario where the very fabric of reality unravels in an expanding bubble of destruction. At the heart of this cosmic horror story lies the Higgs field, an invisible energy field stretching across space that gives particles their mass. For decades, we've assumed this field is stable, like a ball resting comfortably at the bottom of a valley. But startling calculations suggest it might actually be in a false vacuum, a precarious state where the Higgs field is metastable, balanced as if that ball were perched on a hillside, waiting for the slightest nudge to tumble into a deeper, lower energy valley. If that tumble ever happens, whether from quantum fluctuations or a high-energy event, it could trigger a chain reaction with existential consequences. A bubble of true vacuum would form somewhere in space, rewriting the laws of physics within its boundary. The speed of light, the strength of gravity, even the behavior of atoms, everything would change instantly. This bubble wouldn't just sit there, it would expand outward at nearly light speed, erasing the old universe as it grows. One moment, you're sipping coffee on Earth. The next, an invisible wall of annihilation sweeps through the solar system, transforming reality into something unrecognizable before any neurons in your brain could process the change. What makes vacuum decay especially chilling is how little warning we'd get. The bubble wouldn't emit radiation or give off any detectable signal. It would simply rewrite physics at its leading edge, leaving no observable trace until it arrived. Even if it started in a distant galaxy, we'd never see it coming, and unlike asteroids or supernova, there's no way to deflect or survive it. Vacuum decay isn't just an extinction event, it's a cosmic reset button. But here's the twist, this isn't purely science fiction. Particle colliders like the Large Hadron Collider have briefly created conditions where the Higgs field could have destabilized. Thankfully, calculations confirmed these experiments didn't have enough energy to trigger catastrophe, but the fact that we even had to check speaks volumes. Some theories also link vacuum decay to cosmic inflation, suggesting the Higgs field might have been knocked into its false vacuum state during the universe's explosive early expansion. If true, our entire existence could be the result of a cosmic near-miss, a universe that barely escaped collapsing into a more stable but lifeless state. Yet for all its existential dread, vacuum decay offers a strange comfort. If the Higgs field is metastable, it means our universe hasn't lasted long enough to decay naturally, and might not for billions or even trillions of years. That's a reminder of just how young and dynamic the cosmos still is. The same instability that could one day erase everything also underscores a profound truth: the universe isn't frozen in perfection. It's a work in progress, teetering between order and chaos, creation and destruction. And for now, against all odds, it's still holding steady. The universe might be crisscrossed with invisible cracks in spacetime so dense they could slice through planets like cosmic razor wires. These are cosmic strings, hypothetical relics from the universe's fiery birth, when the fabric of reality underwent a phase transition so violent it left behind defects in spacetime itself. Picture the cracks that form when ice freezes too quickly, except these fractures aren't made of water. They're flaws in the very structure of existence, thinner than a proton but with the mass of entire galaxies packed into every inch. What makes cosmic strings so bizarre is how they warp reality around them. Unlike black holes that curve spacetime into pits, strings bend it into sharp angles. If one passed through Earth, you wouldn't feel a pull, you'd witness twin copies of yourself as light bends around the string like a hall of mirrors. And their gravitational influence is staggering. A single string just 6 miles long could outweigh our sun, yet be so narrow that if it circled our solar system, you could thread it through a drinking straw. The hunt for these elusive relics isn't just theoretical. Scientists scour the cosmos for their fingerprints, peculiar double images of distant galaxies that might reveal a string's warped lens, or sudden jumps in the cosmic microwave background where a string's passage left a temperature scar. But the most promising clue comes from gravitational waves. When cosmic strings vibrate or snap, they could send ripples through spacetime strong enough for observatories like LIGO to detect. These wouldn't be the familiar chirps of colliding black holes, but long, steady hums, a cosmic bass note from the universe's earliest moments. Some theories even suggest these strings might be time machines. The extreme spacetime warping near a moving string could create closed time-like curves, loops where time folds back on itself. While the physics remains speculative, it's a tantalizing thought that the universe's most ancient defects might hold the keys to bending time itself. Whether cosmic strings exist remains one of cosmology's great open questions. But if they're out there, they're not just cosmic curiosities, they're fossil evidence of how space-time itself crystallized from the chaos of creation, and perhaps the closest thing we'll ever find to the universe's original blueprints. Black holes might not be the only way the universe handles ultra-dense objects enter gravastars, one of astrophysics' most radical ideas. Picture a black hole imposter with all the gravitational muscle of its famous counterpart, but hiding a bizarre secret at its core. Instead of a crushing singularity, gravastars contain a chunk of dark energy, the same mysterious force accelerating the universe's expansion packed into a thin, ultra-dense shell. This cosmic Matryoshka doll would bend light just like a black hole, trap matter just like a black hole, but never actually form an event horizon. It's the universe's ultimate bait and switch, all the drama of a black hole without the point of no return. Unlike black holes, which funnel everything toward an inescapable singularity, gravastars resist total collapse thanks to dark energy's repulsive force. Imagine trying to squeeze a spring down to the size of a marble. The harder you press, the more it pushes back. That's essentially what's happening inside these hypothetical objects. Their cores wouldn't be empty, but filled with a vacuum energy so intense it counteracts gravity's pull, creating a stable, albeit mind-bending, equilibrium. The surface, a paper-thin crust of exotic matter, denser than anything in a neutron star, yet somehow holding itself together against unimaginable pressures. Spotting the difference between gravastars and black holes isn't easy. Both warp spacetime so severely that light orbits them in identical patterns, and both suck in surrounding gas to form glowing accretion disks. But subtle clues might give gravastars away. Since they lack true event horizons, matter falling toward one wouldn't simply vanish. It would pile up on that ultra-dense shell, potentially creating a faint echo of radiation just before impact. Gravitational wave observatories could also sniff them out. When two gravastars collide, their vibrations might carry a unique signature, like the difference between hitting a drum made of steel versus one made of rubber. The idea remains controversial because it demands physics we've never observed. That exotic matter shell, it would need properties beyond anything in the standard model, with negative energy densities that sound more like Star Trek tech than astrophysics. Yet the theory persists because it solves one of black holes' biggest puzzles, the information paradox. If black holes really destroy everything that falls in, they violate quantum mechanics' rule that information can't be lost. Gravastars sidestep this by never fully swallowing anything. Information just smears onto their surface like cosmic graffiti. Whether gravastars exist or not, their mere possibility shakes up how we think about extreme gravity. They're a reminder that the universe might have more than one way to build a monster, and that some of the darkest objects in space could be hiding the brightest ideas in physics. The Big Bang wasn't just an explosion, it was the ultimate compression event, where the entire universe once existed as a singularity of infinite density packed into zero volume. Picture all the galaxies, stars, and planets you've ever seen, every atom in existence crushed into an unfathomably small point where spacetime itself breaks down. Traditional cosmology describes this as a moment where temperature, density, and curvature all become infinite, a mathematical boundary where the laws of physics as we know them simply stop making sense. But infinity is a concept that makes physicists deeply uncomfortable. Enter quantum bounce theory's radical alternatives suggesting the universe didn't emerge from nothingness but rebounded from a previous collapsing phase. Instead of a singularity, these models propose the universe reached a maximum density dictated by quantum mechanics, where repulsive forces overcame gravity's pull, triggering an expansion we now call the Big Bang. Think of it like squeezing a rubber ball. There's a limit to how small it can get before it snaps back outward. Loop quantum cosmology, one of the leading bounce theories, paints a vivid picture. At the universe's smallest possible scale, the Planck length spacetime isn't smooth and continuous but granular like the pixels on a screen. When the collapsing universe reaches this pixelated limit, quantum effects create a pressure so immense it reverses the collapse, turning the big crunch into a big bounce. This means our universe might not be the first, but one in an endless cycle of expansion and contraction, a cosmic phoenix rising from its own ashes. Evidence could lurk in the cosmic microwave background, the afterglow of the Big Bang. Some bounce models predict subtle, imprint circular patterns or suppressed large-scale fluctuations that would distinguish them from traditional singularity models. While no smoking gun has been found yet, the hunt reshapes how we view cosmology's ultimate question, not just how the universe began, but whether beginning even means what we think it does. The contrast between these models isn't just academic, it's a battle over the universe's origin story. Infinite singularities suggest a definitive start, a moment where time itself flickered into existence. Quantum bounces, however, propose an eternal narrative where time has no beginning or end, only transformations. Both scenarios stretch our imagination, forcing us to confront the deepest mystery of all, that the universe's most extreme density might not be an end, but a doorway to something far grander. Gravity has always been the universe's great architect, sculpting galaxies and pulling stars together in an endless cosmic dance. But in the shadows lurks a mysterious rival, dark energy, an invisible force working in direct opposition, pushing the universe apart at an accelerating rate. This isn't just a gentle nudge, it's a fundamental battle between two titanic forces, one crushing, the other repelling, locked in a tug of war that will decide the fate of everything. The scale of this conflict is almost beyond comprehension. Gravity's influence weakens with distance, pulling objects together with a force that fades over light years. Dark energy, on the other hand, grows stronger as the universe expands, its repulsive effect magnified by the increasing space between galaxies. It's like stretching a rubber band embedded with magnets. The farther apart they drift, the harder dark energy pushes. We see the aftermath in the redshift of distant supernovae, their light stretched by an expanding cosmos, revealing that dark energy has been winning this fight for the past 5 billion years. But how did we discover this invisible force was even there? The story starts with the universe's critical density, the precise balance between expansion and collapse. Too much matter and gravity eventually pulls everything back into a big crunch, a fiery reversal of the Big Bang. Too little, and the universe expands forever, growing colder and emptier. Measurements of cosmic microwave background radiation and galaxy clustering revealed something shocking. The universe's density was close to critical, but ordinary matter and dark matter only accounted for about 30% of the needed mass. The rest, a mysterious, repulsive energy now called dark energy, making up roughly 70% of the universe's total energy budget. What makes this battle even stranger is the nature of dark energy itself. Unlike gravity, which arises from mass-curving spacetime, dark energy seems to be an intrinsic property of empty space, a cosmological constant first proposed by Einstein, then discarded, now resurrected with a vengeance. Some theories suggest it might not even be constant at all, but a dynamic field evolving over time. If that's true, the universe's eventual fate could be far more dramatic than a slow fade into darkness. Dark energy might grow so strong it tears apart galaxies, then solar systems, and finally atoms themselves in a catastrophic big rip. Yet gravity fights back in its own way. In regions where matter is densely packed, like galaxy clusters, gravity's pull still dominates, holding structures together even as the space between them expands. It's a cosmic stalemate on local scales, even as dark energy wins the larger war. Observatories like the Dark Energy Survey and the upcoming Euclid telescope aim to map this struggle in unprecedented detail, measuring how dark energy's push has changed over billions of years. The ultimate outcome hinges on a simple but profound question. Will dark energy's repulsion continue unchallenged, accelerating the universe toward an icy, fragmented end? Or could it weaken over time, allowing gravity to finally regain the upper hand? For now, the cosmos keeps its secrets close, with every distant supernova and galaxy cluster adding another clue to this grandest of all mysteries. One thing is certain: the universe isn't just expanding. It's the stage for the most epic duel in existence, a fight not for territory, but for the shape of reality itself. Nothing in the universe lasts forever, not even the most extreme objects born from collapsing stars. Take black holes, those gravitational monsters we once thought were eternal. Thanks to Stephen Hawking's groundbreaking work, we now know they slowly leak energy into space through a quantum quirk called Hawking radiation. Picture the edge of a black hole, where pairs of virtual particles constantly flicker in and out of existence. Normally, these particle-antiparticle pairs annihilate instantly, but near an event horizon, one can fall in while the other escapes, stealing a tiny bit of the black hole's mass. Over unimaginable timescales, think trillions upon trillions of years, this process causes even the mightiest black holes to evaporate, shrinking until they vanish in a final, explosive burst of gamma rays. Neutron stars face a quieter but no less inevitable fate. Born scorching hot from supernova, these ultra-dense remnants slowly radiate away their heat over billions of years. Eventually, they cool into pitch-black husks called black dwarfs. Cold, dead stars so dense a sugar cube-sized piece would weigh more than a mountain, yet so faint they'd be nearly invisible against the cosmic background. But here's the twist: even black dwarfs won't endure. Given enough time, far longer than the current age of the universe, protons themselves may decay, causing these once glorious stellar remnants to dissolve into showers of subatomic particles. Then there's the ultimate cosmic question: what happens to everything? Current theories suggest that in a future so distant it defies comprehension, even the most stable matter could unravel. Protons might disintegrate, black holes could evaporate, and the universe could be left as a thin haze of particles drifting endlessly in the dark. But some models offer a more dramatic finale. If vacuum decay occurs, a quantum catastrophe where the fabric of reality itself becomes unstable, the very laws of physics could rewrite instantaneously, erasing all traces of the universe as we know it. Yet amid these seemingly bleak forecasts, there's a strange beauty. The same forces that forged these ultra-dense objects, gravity, quantum mechanics, nuclear physics, also dictate their endings. Whether they fade silently or vanish in a blaze of radiation, their stories remind us that the cosmos is dynamic, ever-changing, and governed by rules far stranger than fiction. Even in their demise, the universe's most extreme objects leave behind clues not just about their own fate, but about the ultimate destiny of reality itself. From neutron stars where a teaspoon of material outweighs mountains, to black holes so dense they vanish from reality, we've journeyed through 25 mind-bending examples of how the universe crushes matter beyond recognition. These aren't just cosmic curiosities, they're extreme laboratories where gravity and quantum physics wage war, bending the rules until they shatter. Who knew that the heart of a neutron star might be a swirling ocean of quarks, or that entire planets could crystallize into diamond? That black holes might hide Planck stars rebounding from collapse, or that the vacuum of space itself could be a fragile illusion teetering on the edge of unraveling. Dark stars powered by invisible matter, cosmic strings thinner than atoms yet massive enough to slice through galaxies. Every discovery peels back another layer of how little we truly understand. Even time and space become fluid in these environments, with neutron star collisions forging gold in stellar explosions and magnetars bending reality with magnetic fields strong enough to distort atoms. The universe doesn't just push limits, it reinvents them, proving that density isn't just about squeezing matter, but rewriting the laws of existence itself. So what's your take? Did the concept of quantum foam, space-time boiling with microscopic black holes blow your mind? Or was it the terrifying possibility of strangelets, cosmic contagions that could rewrite all matter? Drop your favorite fact in the comments, and if you're hungry for more cosmic mysteries, hit subscribe. The universe is full of surprises, and we're just getting started.